Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.1.3. Here, we're modding out by a polynomial and then looking for multiplicative inverses. So for instance, let's try to find the multiplicative inverse of x plus 1 bar when we mod out by x plus 3. Okay, so one nice way of doing this is to first think, what's a simpler representative of x plus 1 bar when we mod out by x plus 3? Well, if we divide by x plus 3, we get a remainder of -2, which means that x plus 1 bar can be thought of as -2 bar. Then knowing that, and also knowing that we're working with coefficients that are real, and knowing that -1/2 is a real number, and it's a polynomial, and we can multiply it to get 1, then we can simply say that the inverse of -2 bar is simply -1/2 bar. So we know that the inverse of x plus 1 bar is -1/2 bar. And we did this simply by getting a constant representative for this guy. Now we can't always get constant representatives for things. However, when we do, and we're working with real numbers or something where we can take fractions, that's really nice. Let's look at another example. Now this one's kind of by inspection here, at least the way it's written. We're modding out by x squared, and let's try to find the inverse of x plus r. And if we think about difference of two squares, we can take x plus r times x minus r, and we get x squared minus r squared, meaning that we actually get close to x squared. We're just off by a constant. So that tells us that when we multiply x plus r by x minus r, we actually get to -r squared. Now, once we get to -r squared, what do? Well, it's a constant. And from there, we just take the regular reciprocal once we get to the constant bar here. And so the inverse would simply be x minus r itself, but then multiplied by the reciprocal of -r squared, which is -1/r squared. Let's take a look at this in terms of target inversion, because really, anytime we do multiplicative inverses here, we could use target inversion or the Euclidean algorithm the same way as we did when we were modding with z. Okay, so let's take a look at that. Suppose that we have, we want to, for an example, let's just take an example. Let's suppose that we have something like, and we're modding out by x squared. Let's suppose we have x plus 2. And we want to find out what times x plus 2 will take us to 1 bar. So we're on x plus 2 bar, and we think x plus 2 bar times what gets us closer to x squared. So we can kind of think, okay, x plus 2 times what will get us closer to x squared. Notice that usually when we're finding simpler representatives, we always divide by what we're modding out by. Here it's kind of opposite when we're trying to think this times what gets us close to x squared. So, well, let's do this division. We compare leading terms, x to x squared, so we get x, multiply it through, x squared plus 2x, then we subtract. We get -2x, and then we think, okay, we compare leading terms, we need to multiply by -2, multiply that through, -2x minus 4, then we subtract, end up getting plus 4. Now this means that x plus 2 times x minus 2 plus 4 gets us to x squared, meaning that the product x plus 2 and x times x minus 2 is actually 4 less than x squared. So whenever you do it this way, you think this actually represents how much less you are than where you want to go. So really the result of multiplying by x minus 2, so x plus 2 times that, gets us 4 less than where we want to be, x squared, well, or which is 0. And so that would be -4 bar. Then we have to think, what do we need to multiply to get to 1 bar? Well, we multiply by -1/4 bar, because negative a fourth times negative 4 is 1. So hence we get that this bar times that bar, and we can put the bar over, would be the inverse of x plus 2, which is exactly what we have right here via target inversion. Thanks for watching.